Hey kiddos, so you made it back, welcome. So this lesson is about a technique for fitting models called maximum likelihood estimation. So let's see how it applies to the analysis task of classification. Remember that you started with a set of labeled points whose coordinates lie in some continuous space, and let's say you've decided to build a model of this data in the following way. First, you decide to look for a linear discriminant. As such, you can assign a score, f of x, to every point, where the score is theta transpose x. Theta is the unknown vector of parameters, and that's what you want to calculate. Given the score, you decided to convert it into a soft label by applying the logistic or sigmoid function to the score. It's soft in the sense that the label will be a continuous rather than discrete value. In this case, the soft label at x becomes 1 over 1 plus e to the minus theta transpose x. Its values lie between 0 and 1, so you can, for example, round it if you need to predict a hard 0 or 1 label. The next big question is, how do you choose theta? Maximum likelihood estimation is one technique. Let's walk through the main idea. Start with the labeled data set where y is the vector of m-1 responses or labels, and x is the corresponding data matrix of coordinates. Start with the labeled data set where y is a vector of m-1 responses and x is the corresponding data matrix of coordinates. The responses are the observed class labels. Let's take the values to be binary, either 0 or 1. Let theta be the vector of parameters that represent the linear discriminant. Our convention is that it has d plus 1 entries. That is, there are d predictors plus an additional constant. Let's further assume the convention that the last column of the data matrix has all 1 values. Now suppose someone gave you a model, meaning they gave you theta. You could ask the following question. What are the chances that we would have seen these particular labels under this model? We'll refer to this probability as the likelihood. That's a shorthand for the joint conditional probability of seeing the labels y given the coordinates x and the model parameters theta. Now let's think of the likelihood as a function of theta. The task of maximum likelihood estimation is to find the best model, meaning the one that maximizes the likelihood. So how do we do that? You're going to need two things. First, you need the likelihood. And since you want to maximize it, you need its gradient. So let's start with the likelihood. Remember, it's defined as the joint conditional probability of the labels given the coordinates and parameters. So let's consider the likelihood in terms of the individual observations. Now here's our first simplifying assumption. Assume that the observations are independent. In that case, you can factor the joint probability into the product of per observation probabilities. Let's rewrite that product more compactly as the product from k equals 0 to m-1 of the probability of yk given x hat k and theta. Let's also use the shorthand little lk of theta to denote those individual probabilities. Now, eventually we want to maximize the likelihood. It turns out that trying to do so by directly maximizing this product is hard, mathematically speaking. Now, there are a couple reasons for that. One has to do with taking the derivatives of products, and the other with the fact that these probabilities are tiny numbers. So when you multiply them, they get even tinier. Does that make sense? You might try to think about what I just said in terms of things that you've seen and learned in other parts of this course. So what's next? One idea is to use logarithms to transform this problem into an equivalent one. This idea exploits two properties of logs. The first is that the optimal theta is preserved when you take the log of the likelihood. That's essentially because logs are monotonic, so it can't change where the maximum value occurs. By the way, I keep saying logarithm, but I'm not specifying the base. That is, do I mean the natural log, or log base 10, or log base 2? So in this context, it turns out it doesn't matter because they're all within a constant factor of one another. So I'll leave it unspecified, and if you need a concrete choice, go with the natural log. Now here's another useful property of logs for this problem. The log of a times b is the sum of log of a and log of b. So what does all this mean? Instead of maximizing the likelihood, we'll get the same answer if we instead maximize the log of the likelihood. So let script L of theta be the log of the likelihood, L of theta. Then we want to maximize this log likelihood. Now remember the definition of the log likelihood, and substitute those. That's the log of the product of the individual likelihoods, Lk of theta, which in turn is the sum of the logs of Lk of theta. Now eventually we're going to need the gradient of the log likelihood. That means that we'll need to compute the gradient of this object, log of Lk of theta. So that's what we'll need to do next. So let's take stock of where we are so far for the classification task. At the start of the lesson, we said we wanted to fit a logistic classifier with a linear discriminant to the data. So we needed a way to define what's the best linear discriminant. So to define best, we introduced a criterion called the likelihood, which is the probability of seeing the data given a line. Now our computational task becomes one of maximizing the likelihood. And for a bunch of technical reasons, we decided it would be easier to maximize the log likelihood instead of trying to maximize the likelihood directly. Got it? Okay, if not, I think this is definitely a good place for you to pause so you can reflect on the details of what we just went through. And when you get back, we'll apply the MLE idea to develop a classification algorithm. Okay, so see you soon.